All right, so we're just changing gears again. Let's talk a little bit about properties of liquids. There's two that you probably have heard of before: surface tension and viscosity. So we're going to talk about those. So these both depend on intermolecular forces. So a lot of times the molecular structure of a substance is defined by these intermolecular forces. Some of the physical properties depend on these intermolecular forces. We talked already about two properties. We talked about vapor pressure. Vapor pressure will depend on the intermolecular forces. The stronger the forces, the lower the vapor pressure. And the same thing with boiling point. The stronger the attractions, the higher the boiling point, because the stronger the attractions, the higher the vapor pressure, and I'm sorry, say that again. The stronger the interactions, the lower the vapor pressure, and so the higher the boiling point, because you'll have to get the temperature much higher to get to where the vapor pressure equals the atmospheric pressure. So stronger attractions, lower vapor pressure, higher boiling point. Two additional properties that we're going to talk about liquids have to do with surface tension and viscosity. So what is surface tension? You've probably heard that before. It's if you've seen little bugs sitting on the water, sort of scooting across the top of the water, that's because of surface tension. So what's happening is if you have a molecule here in the center of the liquid, it's got these attractions between all the molecules are equally attracted to each other, and so the pull on this central atom is the same, or molecule. However, if you have a molecule on the surface, it has an attraction to all the molecules around it. However, there's nothing up here counteracting the pull on these molecules. So what happens is that these molecules get just a little bit pulled a little bit more down, and that makes the surface of the liquid a little bit thicker, or have a little bit of almost like a film. You can see that it's kind of thicker, and that's what surface tension is. So actually, there's a tendency for the surface area to be minimized, pull it down, and the energy needed to reverse this technically is what the surface tension is. But that's why bugs can sort of sit on the top of water. The stronger the interactions, the stronger these interactions, the higher the surface tension. This is the reason why rain, where you see beads of water, is because the water's pulling in on itself. The water adheres weakly to the wax. So if you see it sitting on the leaf, it's not attracted to the leaf at all, but it's attracted to itself. So it kind of pulls around, and it gives them that spherical shape, because it's the smallest possible surface, because the tension is pulling the water in close to each other. So that's why we see beading of water. And again, water has very high very strong intermolecular attraction. So that's why water has, you won't see this with all liquids, but water specifically has this high surface tension and has this beading. Similarly, when you see a drop of water come, it also takes that spherical shape, and that's because it's pulling in on itself. You can read that, but I'm just going to go on. So it's because of surface tension. And so again, surface tension is a property of the surface of a liquid that allows it to resist an external force. That's why you can lay a pin on top of water. It can float. Why sometimes you can see bugs floating on the surface of water if they have the right kind of feet. And so, like I said, as intermolecular forces increase, surface tension will also increase. So water has very strong intermolecular attractions, and that's why it has such a strong surface tension. Viscosity is also similarly related. viscosity is really just the resistance to flow exhibited by liquid. So if we put like, you can see here that this metal sphere was put at the top of both of these and let go. One dropped much faster than the other. That means that this substance is less viscous. So this is more viscosity because it's moving slower. And again, that will have something to do with attractions. The stronger the attractions, the more viscous the compound will be. So we know, syrup is greater viscosity than water. So in general, as intermolecular forces increase, viscosity usually increases. Okay, so in summary, intermolecular forces play a large role in many of the physical properties of liquids and gases, things like vapor pressure. So vapor pressure is the only one that's kind of reversed. So stronger intermolecular attractions, lower vapor pressure. Higher intermolecular attractions, higher surface tension, higher viscosity, higher boiling point. So vapor pressure is kind of the one. So let's write that down. Increasing intermolecular forces means a decrease in vapor pressure, an increase in surface tension, increase in viscosity, increase in boiling point. And the boiling is because the vapor pressure, remember, the stronger the forces, the harder it is to pull them apart. So there'll be fewer vapor molecules, which makes the boiling point higher. Okay, so I just went through these. So vapor pressure for liquid, when intermolecular forces, the stronger they are, the lower the vapor pressure is. This shows you a couple of, well, we can look at all three of these things. So look at these. So properties of liquid. So water actually has very strong intermolecular. The molar mass matters a little bit. It's because remember that the higher the molar mass, the stronger the dispersion forces you have. But then we have to be careful because like water here has hydrogen bonding. So it has very strong interaction. So you can see that it actually, well, it has a low vapor pressure because it has strong attractions. So it has low vapor pressure. If you compare, it has a fairly high surface tension relative to all the other liquids, and it has a relatively high viscosity. Carbon dioxide, which is nonpolar, and so it only has dispersion, so it has much weaker attractions. So you can see it has a fairly high vapor, pretty high, actually extremely high vapor pressure. It has a very low surface tension and a very low viscosity. Pentane, which is kind of, I don't know, it's one of the components of gasoline. So it's also nonpolar. So it has weaker attractions than it has weaker attractions than water, but now it's going to be because it's a little bit bigger molar mass, it actually has a lower, so it's weaker, but it's stronger than carbon dioxide because it's got more dispersion, so more dispersion. So it actually has a lower vapor pressure than CO2, but it's still much higher than water. And you can see it, the surface tension is in between and the viscosity is in between. Now glycerol has 3 OH groups. It looks like this. So it has very, very strong, even higher than water because it's got 3 OH groups, and it has a much higher molecular weight. So you can see here it has a very low vapor pressure, very high, actually not quite as high as water, but it has a high surface tension and a very high viscosity. Glycerol, similarly, it's very, very thick. Chloroform is somewhat polar. So anyway, you can see carbon tetrachloride is nonpolar, so it tends to have a lower vapor pressure. anyway, these are kind of in there in the middle, but waters, especially in carbon dioxide and pentane and glycerol, are very useful to see. Again, viscosity increases with increasing intermolecular forces, because the thicker, the stronger the forces, the more resistance to flow. Other things can cause higher viscosity besides intermolecular forces. If molecules are really long and stringy, they can actually tangle. So that could be another factor that we're not really talking about here. So sometimes it may not fit. Remember that the boiling point is related to vapor pressure again, and the intermolecular force, weak intermolecular forces mean low boiling point, and higher intermolecular attractions mean higher boiling points. So those three compounds that have hydrogen bonding, so like remember OH, NH, and FH, they actually have abnormally high boiling points, especially considering that they're such small molecules. So, and that's because of the really strong hydrogen bonding. So if you look, I'm going to show you the some graphs in a second. So water has the highest boiling point of the group 6 hydrides, so group 6A hydrides. And we also see similar trends in 5 and 7. So let me see if I can explain that. So notice here that, remember we said that because of, so let's ignore water here, but if we just look, H2S, H2SE, H2TE, we should be increasing, because molecular weight increases, and we know that van der Waals forces, those dispersion forces, increase with increasing molecular weight. It makes sense that something with a higher molecular weight but very similar attractions should have a higher boiling point, and that's what we see. If water wasn't polar, we would expect the boiling point of water to follow this trend to be somewhere down here, like negative 80. But because of hydrogen bonding, obviously water has a very, very high boiling point. So it's abnormally high. It's kind of unusual. If we look over on this thing, we see the same thing here with the NH3. So the group 5, we can see that SBH3 is higher than ASH3, which is higher than PH3, but then NH3 is abnormally high again. And then the same thing with the group 7A, so HI, HBr, HCl, but then suddenly we jump up HF. Now, if you look at the group 4, because CH4 doesn't involve any hydrogen bonding, C and H are very similar in electronegativity, so this is a very nonpolar molecule. You can see that this is the normal trend. So this is what we would have expected with the other ones. We'd expect the green to come down here and the red to come down here, but they're abnormally high, again, because of hydrogen bonding, which is NH, OH, or FH. So interestingly, water is kind of a miracle molecule. It's because of water we have life on Earth. And as you can see here, water is the only liquid substance other than petroleum that's found in significant amounts on Earth. We know that water is easily converted to a solid or gas under normal Earth conditions. And water has several unusual properties that set it apart from other substances, and that's why it has come to be so important for life. The fact, and I'll talk about this in a second, the fact that the solid is actually less dense than its liquid. I think we all know that water expands as it freezes, which is why you have to be careful about your pipes freezing, because it expands, but it's actually very unusual. It's one of the I don't know of any other liquid that is more dense in the solid phase, or more dense in the liquid phase than the solid phase. So that's a very unusual thing. It has a very high heat capacity. Again, that's because it needs all that energy to break those attractions apart, and so, or to make them move from each other. So the fact that it has a high heat capacity will allow life on Earth. It can store a lot of heat in the water before it vaporizes. It has an unusually large heat of vaporization. It takes a lot of energy to boil water, and it has a very high boiling point, like I said. And this will take us actually into the next chapter. It can dissolve many substances, including polar substances and ionic substances, and we'll get into that in the next chapter, but that makes it a really important molecule. And so again, these properties are all linked to the fact that water makes these strong hydrogen bonds with each other, and that's what makes it so unusual. So let me just explain a few of those things. So again, why is ice less dense than the liquid? We tend to think of solids being closer together, molecules closer together than liquids. But here's actually what happens, and it has to do with hydrogen bonding, and it has to do with the shape of water. So here you can see, here's liquid water, where there's hydrogen bonding happening. Some of they're breaking, they're forming, they're re-breaking, they're reforming, and kind of moving about each other. As they get slower and slower, what happens is that these molecules sort of line up, sort of like this hexagonal shape. It's because of the shape of water and because of the size of water and because of the hydrogen bondings. It ends up making this sort of hexagonal shape. And that's kind of why you see water, like snowflakes, kind of have that shape too. But anyway, it's what you see is more empty space. So because they freeze in this kind of weird shape, and that all has to do with hydrogen bonding, it ends up with more empty space in the solid than it does in the liquid. So that's why ice is less dense. So there's little air pockets. Because of the low density of ice, means that it forms on top of liquid rather than from the bottom, and so it will insulate the water below it and not make it quite as cold, and so limits further freezing and allows a lot of those fish to stay alive, because it keeps the water a little bit warmer than it might be otherwise, and the water won't freeze. The fact that the heat capacity is so large means that it requires a lot of energy to raise the temperature of water just by 1 degree. And so, so water doesn't just boil away. It takes, it moderates the Earth's temperature, it traps the heat during the day and releases it at night. And so again, it moderates Earth's temperatures, and it keeps temperatures pretty consistent, and they don't vary as widely compared to other planets. You know, like Mercury has very hot in the day and it's extremely cold at night, and so again, it moderates the Earth temperature. The fact that water has such a high boiling point and high heat of vaporization means that it won't vaporize very easily, so that's why we have mostly liquid water at normal Earth temperatures. And this is very unusual because water is such a small molecule, such an important molecule. A couple other things, the fact that water has this high surface tension is what creates capillary action. So you can see here that the water gets, adhesion gets stuck to the side of the capillary and will pull. So because it sticks to the side, then it actually pulls the water up a little bit, and so cohesion pulls it up into a capillary. And of course, we know plants use this kind of system to pull water up into it. So adhesion builds up on the walls. The high surface tension means it pulls up the water. Also, water is a universal solvent, and that's going to be really important because it's polar, it can dissolve other polar molecules, but because it's polar, it can also dissolve. We already talked about solubility and what can dissolve. Lots and lots of ionic compounds can dissolve in water, which allows for nutrition of plants and us as well. So because living cells are mostly water, the need for nutrients and other compounds are able to get around in the liquid. So these are just some interesting little tidbits about water. All right, so here's a few things that you should keep in mind when looking at intermolecular forces. Remember that hydrogen bonding is the strongest intermolecular force, followed by dipole-dipole interactions, and then London forces being the weakest. However, keep in mind that all intermolecular forces are still weaker than actual bonds, like ionic bonds or covalent bonds. London dispersion forces operate between all molecules, whether they are polar or not. So what that means is that even if it's a polar molecule or a dipole-dipole molecule, or they all have London dispersion forces. And so that's when, if everything else is the same, a larger molecule will have a higher boiling point because it has stronger dispersion forces. And so, like I said, London dispersion forces increase with increasing molecular weight, and also increase with longer, skinnier molecules. So we can then form some guidelines to use when comparing physical properties of different compounds. So we can look at a couple of compounds and decide which one might have the higher boiling point, or which one might have a higher vapor pressure, or things like that. So what we're going to do is, if we compare two molecules and they have similar weights and shapes, and we'll talk about shape in a minute, then this means they have approximately equal London forces because they're the same weight. So a more polar molecule will have stronger interactions. If the molecules differ in molecular weight, London forces become more decisive, and a heavier molecule will have larger dispersion forces, meaning stronger interactions. Now, I can only help you compare apples to apples and oranges to oranges. So sometimes if you've got a molecule that are very different in size, and some are polar and some are nonpolar, like for example, gasoline is very nonpolar. However, it's a huge molecule, and so I don't know if gasoline happens to have a higher boiling point than water, and so we can't compare it. So even though water is polar and gasoline is not polar, because it has such strong dispersion forces. So I can't ask you something that would be really hard to compare, but I can compare apples to apples, like I said. So hydrogen bonding, being the strongest attraction, is the most important factor, and I'm going to go over an example of what I mean in just a second. All right, so for example, list the following compounds in terms of decreasing boiling point. So let's think through that. So we want to go from highest boiling point down to lowest. And let's think about what that means in terms of attraction or intermolecular attractions. So the higher the boiling point means the stronger attractions. And the lower boiling point will be the weaker attractions. So higher boiling point. So we want to go from in decreasing boiling point, so from higher to lower. So that means we want to list these compounds in terms of start with the strongest interactions down to the weakest interactions. So now let's look at these molecules, and you might have to go back and review a little bit from the polarity and trying to determine if a molecule is polar or nonpolar back from last semester. Hydrogen, because it's just a molecule of H bonded to H, because they're the same element, this has to be nonpolar. CO is a C bonded to an O. And you can look up electronegativities. This happens to be a polar molecule, but it's not hydrogen bonding, right? So it's dipole-dipole. HF is a bond, and we know that this has hydrogen bonding because it's one of the three O-N or F. Neon isn't even bonded, it's an element, so it's just by itself, and so anything just by itself can't have any kind of polar bond, so it's nonpolar. Or in other words, London dispersion. Now, if we look at the molecular weight, this one's not too bad. Well, Yeah, let's say. So already we know that hydrogen bonding, this has a weight of about 20. Let me look at my periodic table. Fluorine is 19 and hydrogen is 1. Carbon is 12 and oxygen is 16. So that's about 28. This is 2 and neon is 20. So you can see these three are really similar in size. And they're very different. So we've got nonpolar, hydrogen bonding, and polar. So because they're already the same size, and so hydrogen bonding should be the strongest. So I would think HF should have the highest boiling point of all of them. Then I would expect CO to be next. Now, both of these are nonpolar and London dispersion, but now we can use the difference between the molecular weight. So neon, with being heavier, should have a stronger attractions than hydrogen, which would be the weakest. So I would expect this to be my order from highest boiling point to lowest boiling point. And again, there may be some differences, but this is what I'm asking you to do. Again, we can't compare everything apples to apples. The only two we could compare here were that they were very different. These three were all similar, and so we decide between polar, non-polar. But this is what I would, the kind of example I might go through, ask you on a test. All right, so again, we look at relative strengths of intermolecular forces. Hydrogen and neon, like I said, are both nonpolar. Hydrogen is much smaller. So neon is going to have slightly stronger attractions. CO is dipole-dipole. HF is hydrogen bonding. So this is just going through exactly what I just said. So the stronger the forces, the harder the molecules are to pull apart, meaning the higher boiling point. So we want to list compounds from highest to lowest boiling point, and so we list them from highest to lowest forces. So just be careful, make sure and go through all the different parts. So like I said, this is the order of highest boiling point to lowest boiling point. I think I have one more example. Yeah. So list the following compounds in terms of increasing boiling point. So just be really careful about what's being asked. Increasing boiling point means lowest to highest, which means weakest to strongest. So here I've given you kind of the structure here, and note, oh, it doesn't tell you somewhere. Oh yeah, here it does. So the big one is carbon. Let's see if I can do the yellow here. This is carbon, 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 carbon. Notice that the O is the red is oxygen, and the blue is hydrogen. So you should be able to look at all these. You don't have to draw them in, but anyway, I want you to notice a few things. So this has a O. Let's go back to this color. This has a OH. So this has hydrogen bonding. This also has hydrogen bonding, and it actually has 2 hydrogen bonding. So hydrogen bonding. So if you compare these two, the fact that this has a larger molecular weight and has 2 OH groups means that this is going to be the stronger of the two. This is going to have stronger. However, because the hydrogen bonding, this is still going to be pretty darn strong. Both of these are nonpolar, and you know, like I said, we can go back and look at electronegativities, but I'll tell you that it helps to keep in mind that carbon and hydrogen, if only you see carbon and hydrogen, it's pretty much nonpolar. So if you need help, you can look back at electronegativities, but in general, C's and H's are nonpolar. So this only has London dispersion forces. This only has London dispersion forces, and then we have hydrogen bonding and hydrogen bonding. Since those both have London dispersion, we need to compare the size, and this is 24. This has a molecular weight of 30, and this has a molecular weight of 16. So clearly this should have the stronger London forces. All right, so if we want to list them from weakest to strongest, then D should be the weakest because it's London dispersion and the smallest, and then C. And then the highest should be B because that's got 2 hydrogen bonds and it's a larger molecule, and then A is a little bit weaker. So that should be my order. All right, let's do one more here. List the following compounds in terms of increasing vapor pressure. Now again, be careful. So we want it increasing and we want vapor pressure. So we want the highest vapor pressure. Oops, we want the lowest to the highest vapor pressure. Now vapor pressure, remember, is the opposite. So the lowest vapor pressure means the strongest attractions. Strongest. So we want the strongest interactions to the weakest, because high vapor pressure will be the weakest attractions and low vapor pressure will be the strongest. So what we want to do is get this in terms of strongest to weakest. All right, so again, let me point out a few things. We have OH, so this has hydrogen bonding. This is London dispersion because it's only C's and H's. This is also London dispersion because it's only C's and H's. Now notice that this one has a nitrogen, but there's no NH. So this is dipole-dipole because it has so a CN bond is polar, a CN bond. So it's polar. What's DT? Dipole-dipole. Dipole-dipole, or in other words, it's polar. So hydrogen bonding, and this is also the largest molecule. Now there are some situations where that may not be true, and we're not going to get into that. Like I said, I'm only going to give you examples that can make sense. So out of these four, the strongest attraction should be B, because that's hydrogen bonding, and then the next one should be A. And these are similar in size, so hydrogen bonding and then nitrogen. And then this is actually a little bit smaller also, so that helps. So C, and then the weakest should be D. So B, A, C, D. Hope that makes sense.